So let's discuss atmospheric pressure in more detail. So what exactly is atmospheric pressure and where does atmospheric pressure come from? Recall that our atmosphere is not simply empty space. It's composed of many different types of atoms and molecules. And just like in a liquid, our molecules in the atmosphere are also capable of exerting a pressure. So liquid and gases fall into a category known as fluids. And so our atmosphere, the molecules in the atmosphere, are capable of creating or exerting fluid pressure. Now, the actual pressure within the atmosphere differs and depends on things like location, temperature, as well as weather. But if we examine the atmospheric pressure at sea level, we see that on average, the pressure is equal to this quantity. 1.013 times 10 to the 5 newtons per meter squared. And because 1 Newton per meter squared is equal to 1 Pascal, this quantity is also equal to 101.3 kilopascals. Now, these two quantities are both defined as 1 atm. So 1 atm of pressure is simply 1 atmospheric pressure, which is the pressure at sea level. Now, another type of unit of measurement that we should be aware of is bar. 1 bar is equal to 1.000 times 10 to the 5 Newton per meter squared. So we see that 1 bar is slightly below 1 atmospheric pressure. In fact, 1 atmospheric pressure is equal to 1.013 bar. Now, for example, let's suppose somebody asks you to calculate what 2 atmospheric pressures is equal to in terms of Newton per meter squared. Well, if 1 atm is equal to this quantity, then 2 atms must be equal to 2 times this quantity. And we can easily interconvert from this measurement to this unit to this unit. So, we see that our atmosphere, the molecules in our atmosphere are capable of creating this fluid pressure, which is pretty large at sea level. Now, the question is, if the pressure created by the atmosphere at sea level is so large, how could our bodies withstand this pressure? In other words, why aren't we squished? And in fact, how does our human body resist this high pressure, this high atmospheric pressure? Well, the answer to that question lies in an examination of the cells of our body. The cells in our body are able to create an internal pressure that is almost the same as the atmospheric pressure. And so, in fact, we don't actually feel any pressure because our cells are capable of creating that pressure. Now, let's go into gauge pressure and absolute pressure. So gauge pressure is simply the pressure as read by a certain instrument, for example, a tire gauge, which reads the pressure found solely in that tire. Now, there's also something known as absolute pressure. The absolute pressure of anything is simply the sum of the gauge pressure and the atmospheric pressure. So to look at an application of this equation, let's look at the following example. If a tire gauge measures a pressure of 200 kilopascals, find the absolute pressure in kilopascals. So we simply use this formula and recall that at sea level, our atmospheric pressure is 101.3 kilopascals. So 101.3 kilopascals plus 200 kilopascals gives us an absolute pressure of 301.3 kilopascals. Now, let's look at another interesting example that involves atmospheric pressure. So, let's suppose you place a straw into a cup filled with water. Now, you then place your finger over the top of the straw so that some air is trapped between your finger and the water. So it's trapped in this section in the straw. When you take the straw out, the water remains inside the straw. Now, the question is the following. does the air in the straw have a higher pressure than the atmosphere? In other words, when we take our straw and we place our finger on that straw and we take that straw out, that water remains in that straw. And that's because there is a pressure buildup in this space. Now, the question is the pressure in this space greater, equal to, or smaller than the pressure found in the atmosphere? Well, to answer that question, let's find all the forces acting on our section, on our volume of fluid. So we have three forces acting on the fluid. The first force is the force of gravity, which points downward along the y-axis. The second force is the force created by the molecules found in this space, in this section. And that force is simply the pressure in this section multiplied by the cross-sectional area. Now the third force is the force that's created by the atmosphere, by the molecules found in the atmosphere. And this force is given by the pressure in the atmosphere multiplied by the cross-sectional area. And so because when we raise our straw, the water remains stationary, that means the water is in static equilibrium. So the net force along the y-axis acting on our volume of water has to sum up to 0. So we choose going upward to be positive and downward to be negative. So we have one force pointing up and two forces pointing down. So our force due to the atmosphere minus the force due to the space minus mg. And so we see that our pressure of the atmosphere is higher than the pressure inside this section because this whole quantity is equal to the sum of these two forces.